All right. Hello, everybody. So let's talk a little bit. The first thing I want to talk about isn't the problems. I want to talk about IXL. So, all of my Accelerate students, I want to make sure that you understand because it is vitally important to get any of the incentives to number one, attend every day. So, I'll put that right here as a little bullet point attend every day. You must satisfy all of these to get bonus points and additional attempts on assignments, and then the reward potentially at the end. Still coming up with the big reward. So attend every day, so actually show up. Now, I'm going to put this as separate, even though you'd think it'd be implied, but participate every day. Participate every day. And I'm going to put in this, what I mean by participate is ask questions in chat or Desmos. Answer questions. Remember, everybody is at different skill levels in Accelerate. And so your questions are not going to sound stupid or you shouldn't feel like they're that you should be embarrassed or anything like that. Everybody's in different spots, and likely you're going to ask a question that other students want you to ask. They might want to think, like, maybe I should ask this question, but they often get nervous and their heart starts pounding, and then they don't do it. And I learned I had to be the one to ask and answer questions sometimes. Now, I want to point out, if you're one of my enriched students, the ones that that already know the stuff, kind of give the other students a chance. If you already know the answer and you're very confident, kind of give the other students a chance and then answer, just to help us out. I don't want one or two people dominating the conversation. But the asking questions is the most important part. So participate every day. Ask questions, answer questions, kind of have discussions, things like that. There's a lot more for participation as well. But just sitting there grinding it out doesn't work. But here's the big important one. You got to complete the IXL diagnostic. You got to complete the IXL diagnostic. And by this, that means let's not just practice pre-K skills, because some people do that, then that's not going to count. So what we need is to complete the IXL diagnostic. So the skills need to be a dot with a star. Not a range. And to do this, you need to hit step into the arena. My spacing's all kinds of wonky. Step into the arena. You're going to have to hit step into the arena. If you're just practicing the skills below, then you're not doing the diagnostic. And once you have completed the diagnostic, I really just want 20 minutes a day practicing diagnostic skills and STARD skills. If you're seeing a lot of pre-K stuff, first grade, second grade, that stuff's not going to count. That stuff's not going to help almost anybody. So make sure that you finish the diagnostic so that it actually recommends skills that are useful to you, so you can actually grow and learn, because at the end of the day, we want to pass the class well, and we want to pass the leap, and we want to move on and actually make it to where future math classes aren't overwhelming. So I just want 20 minutes a day from you practicing diagnostic and STARD skills. It's important to do this because we'll be tracking it in my little attendance and engagement tracker, and you won't be eligible for all the extra perks. Now, one thing that I would like at the end of it is get the diagnostic done early, because if you increase diagnostic score by 40 points before the end of the year, So let's just say you start with a 240 and you end the year with a 280, or if you start with a 920 and you end this year with a 960, increase diagnostic score by 40 points by end of semester. We're going to have a big reward, I'm still deciding what it is, and I have to talk and convince the other teachers to allow certain things. So, but we're going to have a reward at the end of that. But anyway, and remember, non-engaged students will be removed because to open up space for students that will participate. All right, now let's talk about this stuff. This part right here, we want to talk about intervals, inequalities, piecewise functions, all that kind of stuff. There's a lot going on here. So this is what we want to go to. We want to get to this, being able to make these and read these. Now, they look really difficult, but they're really not that bad. It's actually pretty easy when you get the hang of it. So what I'm going to do real fast is I'm going to make sure that we actually understand our graphs. A lot of students feel like there's a lot of mystery and magic in graphs, but there's really not. So we can look at the number line and understand what it means. So, we have our 0, we have our 1, we have our 2, 3, and then it goes on. And normally we wouldn't do a lot of these, but, whatever. This is fine. And then we have the exact same thing over on the other side, which I realize I can't reflect it. So -1, -2, -3. This is not going to look very good. But it's not very well spaced. But let's just say that this number line is measuring x. Okay, we're just calling some variable, and a variable can be numbers, and we're just going to call it x. And to understand something very important, we could actually do this exact same thing again. Just kind of copy it right here. We can do this exact same thing again, and I'm going to make it red for funsies, and call it y. So if we were to have two numbers, an x and a y, we could have two different number lines. And we could say, maybe we know that x is equal to 2. There you go. That represents x equals 2 because we've decided to say x is equal to 2. That's what that would look like. Maybe we say x is instead equal to 5. Well, that's easy. We just put a dot right there. The dot represents equal. A closed dot represents equal. Now, that's going to become a little bit important because we want to talk about inequalities. An inequality, if x is greater than or equal to 5. So a lot of students say that little line at the bottom of it. That little line just means equal. So whenever you're reading this, if I say, should I use a closed or an open dot, and you say closed dot, and then I say, why is it a closed dot? And you say the little line at the bottom, try to change your language so you understand each time and reinforce it that it's because it can equal 5. So what I mean by this, when x is greater than or equal to 5, the first thing we do, let's deal with that equal part. That equal part is just saying it's a closed dot. Now, x is every number, can be any number greater than or equal to 5. We've already taken care of the equal part, so the greater than, all the numbers to the right on the number line are greater than. That's all it really means. All the numbers to the right, let me change it to something like this. All the numbers to the right are greater than. That's all it means. So you go right. And the solid line, much like this over here, the solid lines and curves just represent an infinite number of points. Now, a lot of students, they want to only think in integers and whole numbers. But we have so many more numbers than that. Because I want to show you what it looks like when x is just strictly less than. Strictly less than. Now, that line only means the equal, though. It only has to do with a closed dot. So you don't have the equal sign right here. You don't have that line at the bottom of it. So we know, number one, we can start off with x is not equal to 5. So we'll do an open dot. An open dot means that it's not equal at that point. and x is less than, and I happen to know that I just goofed that because my orientation lock is turned off. So I happen to know that all the numbers to the left of 5 are less than 5. And that's how I know to go to the left. Well, I'd straighten up the line, but it's not super important right now. So that is x is less than 5. Strictly less than. So we have this open dot right here. So a quick review of that. If we have the symbols greater than or less than, and they are equal, like this. So if it's any of these, this or this or this, closed dot. And if it's this or this, it looks like a smiley, open dot. Basically, anytime we do not have the equal sign part, it's an open dot. Anytime that we do, like these little lines at the bottom, that means that it is a closed dot. Okay. Now, one more thing. If we have a greater than or equal to, so greater than signs, and I'm talking about if x is on this side, okay? Now, you could put x on the other side and just read it backwards to say that that's less than, but that's not what I'm talking about. Let's say an example would be something like this. Okay, x or y or whatever is, x is greater than, then these are going to go to the right. It's going to go, the line that you draw, no matter where you draw it, is going to go in the direction where the numbers get bigger if it's greater than. And similarly, it's going to go left if it's less than. So, and again, I mean when x is on the small side of that symbol. If x is on the other side, it's still greater than. The symbol is not what matters. It is comparing values. That's all it's doing. So when I have like x is greater than 5, the reason this is greater than is not because the symbol is oriented this way. It's because the bigger side is facing the x and we're comparing it to the 5. That's simple as that. So there's no magic happening for any of these things. But that's how those inequalities work. But I want to kind of relate our number line with this graph over here. Because I want to show you that these graphs right here, x and y, whatever, it's just two number lines on top of each other. That's all it ever has been. It's like that meme always has been. It's like I took that and I put it right here where the 0 marks are on top of each other. That is your Cartesian plane. Oh, I wish I had gotten rid of this first. That is your Cartesian plane. So in this case, I know the numbers are all wonky and weird, but this is y. And so if I wanted to say that with our points, let's say we're trying to graph the point, any of our points, they're always x, y, and then y. And so if I'm trying to graph 3 and then -2, this is a point right here. So this right here is delineated as a point. We're going to have another situation where this could be an interval, but we're not talking about an interval yet. This is what we've been used to as points. So if I were to do that, I'd say, well, my x is 3. Okay, so my x is somewhere, like we could do it like this, but we don't want to do it on the axis because we've also got our y. We want to have a point that is both of them. So really, it's like we're doing this. So let's do our x part. I'm just going to do it in this, all in a different color. Pink is fine with me. So like a dotted line. Everything right on this vertical line right here has the x coordinate of 3. And similarly, with our -2, everything on this dotted line has the coordinate y is equal to -2. Because it's like that intersection of two number lines. So, when we're looking at this thing, we can say that y is -2 on this line, and x is 3 on this line. So just to remind you about how points work. And then we're going to graph, the point is when it equals that little intersection. Now, you don't need those dotted lines or anything like that, but that's all that's really happening here, forever and always. Just as quick reminders of how graphs are working. Just so, because a lot of times students try to make magic happen and it ends up making them just paralyzed, not knowing what to do. Now, this is called a piecewise function. This is called a piecewise function. So notice we use inequalities here, but you can also use interval notation, which I'll talk about a little bit later because I want to relate it to our inequalities first. So this is like we're used to dealing with functions that are like f of x. So you've got your input right here, and this whole thing is your output, and it has certain relationships between our input and our output. Your x is always your input, and your y value, or your f of x value, is always your output. So we're used to looking at stuff like this. And if we plug in a bunch of x's, we can find a bunch of y's. So we plug in a bunch of inputs, we can find a bunch of outputs. And we end up getting something that looks like this right here. This thing right here. Now, this would go on forever, but this thing right here just kind of limits it. That's actually this branch. The reason it looks like a little parabola or a little U shape is because it is a parabola. It's just part of it. And we've said right here that for all of the x's in between -1, so I'll just kind of do like that. That's x equals -1. Everything on that line is x equals -1. And 2, so everything on this line right here is 2. For every x in between -1 and 2, including -1 and 2, because here's an equal sign, it will look like this thing. It'll look like this function. And that's all this thing is saying. It's just saying that this function has a bunch of different pieces. So it could be that somebody is, is in a car and they're steadily speeding up at a constant rate. And it looks like this linear thing right here until whatever x is less than until -1, not including -1. And then suddenly they skip in their speed. So maybe they put their nitro boosters on. Or they suddenly start, they get really fast in this little disjointed part right here, and then they brake and then speed up, and that's modeling their speed between x is equal to -2 and 2. And then after that, they somehow, I don't know, so a bird comes in and picks it up. I don't care about the real world example here, but the main idea here is that it just looks different from one moment to the next on this graph, whatever our input is. And piecewise functions are actually more common because you're less commonly finding shapes that look like that, and you're more commonly finding like a house that has something like that, and then something like that, and then something like that. I don't know what that could be. That could, for all we know, that's a Louisiana pothole. It probably is a Louisiana pothole, considering how many I've seen. But the idea here is we want to be able to read these and create them. So we're just saying that between certain input values, our output looks like that. And so this thing tells us all about that. So right here, when x is less than -1, so let's draw the line x equals -1. That's this pink line right here. That's the line x equals -1. Every single point on that line has the value x equals -1. For every x less than -1, so that's to the left. So if we look at just this number line, just think about our x's, because we didn't say anything about our y's right here, it's going to be every single x to the left of this. That's all it means. So every single x to the left of this. I need this bigger. Okay? And I'll say that I did that like that. So that's that. And then it's going to look like y equals x. Our output equals x. And that's why it is a line with a slope of 1. Switching colors a little bit. Let's look at this one right here. So this is saying for every x between -1 and 2, including the endpoint. So again, we've still got that pink line right there. We've still got this pink line right here at 2. We already did that. So everything between this. So just to make sure you understand this part, so we can look at each one of our parts individually. Let's look at x is greater than or equal to, because the bigger part's facing the x. X is greater than or equal to -1. Well, let me draw that line. Greater than or equal to on just thinking about a number line. That's why it's important to learn it. Greater than or equal to would look like this to this. So here's all of the x's greater than or equal to -1. Notice we also have this other part of it. So I'll do like this. We have this other part of it that I'll do in blue because it's going to be a cool effect in just a second. X is less than or equal to 2. So that would be this to this. So that is the, on the number line, every x that is less than or equal to 2. And look at that part where they both overlap. See how it turns this weird grayish green type thing? That is the intersection. That is what this is giving you, the whole thing. Get rid of both of these. That is what this entire thing is giving you. So that's how you represent it. You're basically finding the intersection or the and statement where they are both true at the same time. We don't care about what's happening over here. We don't care about what's happening over here. We just care about the intersection point when we had one of these compound inequalities. But either way, in between those two values for x, it looks like this. It looks like this. And that should look like a parabola that has been translated up 1. All right, and last but not least, I've already drawn the pink line. When x is greater than +2, so this is the line on the number line, x is greater than, so open dot, +2. So that's all of these things. X is equal, y is equal to -1. Our output is -1. Our function gives us -1. And that's why this line is a horizontal line. It's because no matter where you are on this, your output value, no matter what your x is after that point, your y value is -1. So a lot of times this can be a struggle because students, they want to make magic happen, like I'm going to say a million times, and they don't understand the difference between their x's and their y's, and they don't know how to navigate these graphs. Now, what if we wanted to build one of these? What if we wanted to build one of these? Well, let's do it. Let's just come up with one, okay? I'm going to do, what's a good color? One of my favorite colors is teal. So we've used f of x and g of x a lot. So, I mean, f of x and h of x a lot. So let's use g of x. And let's say that g of x, we've already done linear and all that kind of stuff. So let's just come up with something. Let me come up to this for ideas. Okay, well, let's do our little kind of half set notation stuff. It's really just saying that we've got a bunch of branches it could be, a bunch of possible things, a bunch of different pieces. And we're going to label in this part right here, no matter what we put right here, it doesn't matter how many pieces we have, we're going to put in right there, we're going to put what the actual function is going to look like. So normally with a regular non-piecewise function, a regular just y's function, we would put some algebraic expression. In this case, with a piecewise function, since you have different pieces, you'll put the algebraic expression for the output right here. So this will be whatever your y value is going to be, however it relates to your input. So let's say that it is x squared minus 2, no, plus 2. Let's just do plus 2. So that is the output. A good way to read this is your output is equal to this if, and you can put the if right here if you want. You don't have to, but if it's not there, it's implied. If x is less than or equal to -2, okay? And so that's the first output. That's the first piece. X is less than or equal to -2. Even if these aren't in order with your things, it will still always work as long as there's not a lot of overlap or any overlap. Overlap is going to make it not a function anymore. Remember, if your input has more than one output, it's not a function. And then let's say that it looks like, let's see, x plus 2, x plus 8. Let's do x plus 8. I think x plus 8 will go pretty well if x is between. Let's do one of those between things. If x is greater than -2, notice I didn't double up my equal signs. It's not going to be greater than or equal to because I want it to be kind of defined. We'll see what happens. If x is greater than -2 or less than and equal to 4. Yeah, that'll do it. All right. And then let's say that it looks like let's say our function spits out -x -x plus, what would be something that would be nice? 16, something like that. If, and again, you don't have to have this if x is greater than, strictly greater than, just for funsies right now, 4. Let's see what this looks like. Regardless of how I made it, it might not come out exactly how I wanted, but it's going to be graphable. So let's start graphing some. So let's pick some x's. You know, if we want to graph this normally with our vertex form and all that kind of stuff, we can do that. But let's just pick some x's. We know this is going to look parabolic, so it's going to be a quadratic. So let's just pick some x's that are less than this. So let's try x's, let's just try x's -2 first. So if I plug in x equals -2, I get -2 squared plus 2 because I'm going to look at this branch. No matter what x's I'm picking, I need to make sure whatever I plug in goes into the correct branch. So if I choose x equals -2, I look at this and I say, all right, this is the only branch where x can be equal to -2. So I'll just plug that in. And what I'll get is -2 squared is -2 times -2 is 4. So we're going to get 6. All right, let me graph that point. When x, so we have the point, x was -2, y was 6. So when x was -2, y was 6, so that's that point right there. From the origin, I went to the left 2 because x was -2, and up 6 because y was 6. Now let's find some more to the left. Let's find some more stuff to the left. So I really only need to change this part. So let's just try -3. Why not? Okay. Let's try -3. So I get -3 times -3 for this part is +9 plus 2 equals 11. So x is equal to 11. I mean, y is equal to 11 when x equals -3. So when x is -3, y is equal to +11. So I'll do like that. Sometimes those little guiding lines are nice for trading wheels. Now this isn't going to look too much like a parabola because it isn't shifted that much. This is going to look to the left part of the parabola. You're not going to get this cool U shape unless you get this entire thing like that. But we know that we're not going to be able to graph to the right of that. And, you know, we'll graph some more points and we'll kind of just do the parts to the left. And then it'll look like the far left side of the parabola. Now, again, if this wasn't limited and a piecewise function, this would look a little something like this. But we're kind of cut off because it doesn't look like this piece anywhere except for when x is less than or equal to -2. All right, well, I'm going to change the color of this just so that it looks fancy, like I know what I'm doing. I'm kidding, I do. I definitely do. Miss Snyder's twin, remember? So let's see. we have x plus 8. So I want to try some stuff in here, in this little area right here. So x plus 8 if x is between -2 and 4, not including -2. So really we do an open dot at -2, whatever that is, but let's try plugging it in. Let's try plugging in, see where we need to do our open dot when x is -2. And again, we're just picking these things. There's nothing fancy about these things. We can just say x is -2, and we're going to plug it into this branch because we want to find the open dot. So let's see. We always plug in our endpoints at the very least, and then we do stuff in between if we have that. I like starting off with my endpoints anyway. So when x is -2, we get -2 plus 8 equals 6. Hey, what a coincidence. I actually set it up on purpose that way. So if this wasn't here, then we would just put an open dot. When x is -2, y was 6. So at the point -2, 6, we'd put an open dot if that part wasn't there. But that point, that dot is there, so it'd be like that. But since there's already a closed dot there, we wouldn't need to do that. We can put an open dot around that, but it's still closed technically. I'm just color coding it so it doesn't look the same. Just so you understand the process of each one of these. What happens if we try x is equal to -1? Because that's to the right. That's to the right of our thing. So when x is equal to -1, we get -1 plus 8 equals 7. So when x is equal to -1, we get y is equal to 7. And similarly, we'll keep doing this, and we have a slope of 1. Maybe you want to use slope-intercept. And we'd keep doing that until x is equal to 4. Maybe we plug that in. We get 4 plus 8 equals 12. So when x is equal to 4, y is equal to 12. And, if you had to use slope-intercept, it would look like that. Now we just have to make sure, can it equal that point? Yes, it can. It's got that little line at the bottom. That means that it is equal. It's less than or equal to 4. Now let's try our other branch. And these don't take this long normally. Most of this is explanation. So just be wary of that. Don't get overwhelmed. Let's try this last branch. I'm going to make this one purple. All right, let's plug in our endpoint. We know it can't equal, so it's going to be an open dot. So negative, and we plug in x equals 4 plus 16 equals positive 12. So when x is equal to positive 4, y, or when it would be equal to that on this branch anyway, even though it can't actually equal, our y is 12. So let's go over here again. Let's put an open dot at 4, 12. Well, that's right here. Now, when you put an open dot on top of a closed dot, it just becomes a closed dot because it's already included in part of it. But for this branch, we're going to put an open dot. All right, well, let's put some more above that. Now, we could do slope-intercept for a line to make it faster, but whatever. So to the right of 4, we can just pick 5. Again, I'm picking whatever I want. So negative x, so negative 5 plus 16 equals 11. Boop. And if we use slope-intercept and use our rise over run of -1, it's right here. It's not written, but it's implied 1. We get something like that. And this goes on forever because it says it's all of the x is greater than. So this is how you create a piecewise function. Now this looks like a line, but we've got to remember where it came from. It is a quadratic function in that branch. It's just that we saw the far left side of it. This one was nicer because this one was in between, but this one was the far left side. So just be careful of that. But our main thing is we want to understand that piecewise functions are just our normal functions. We've just kind of restricted our domain of each one of them. So we're saying from a certain x or input to another x or an input, the function looks like this. And then we just pick points in between that and to the endpoints. We just graph them, and we graph it normally. But it's going to look like different functions, and this is common in like acceleration and all that kind of stuff. So let's talk a little bit about that interval notation stuff. So you might see something that looks like this. x is trapped in between 4 and 2. So in this case, this is saying x can be any number between 2 and 4, including 2 and 4, so equaling as well 2 and 4. Now, if we want to do this in interval notation, there's another way to do it other than doing it as an inequality. We can do it with square brackets. Square brackets means that it includes the endpoints. And that's the only thing that matters right here in this thing. We're going to have something that looks like this with a comma. And this is not a point. And even when we do parentheses, we'd say the interval. X is the interval from something. We'd always use some context to say if it's an interval or a point. So it's going to go from the lower value to the higher value. That's it. The little square brackets are always if it can equal. Let's contrast that a little bit to if we had -5. If x was stuck in between -5 and 10. Does it really matter what your numbers are? And it only includes the end point of 10, not -5. So again, let's see what happens. So the far left side, the lower number, is going to go right here. And the higher number is going to go right here. Now we need to figure out if we use brackets or parentheses. So if it's not equal to, see this does not have an equal to, it's parentheses. If it is equal to it, brackets. That's it. Brackets is if it's equal, parentheses if it's not. And the only other real thing is if you have x is greater than or equal to like 5. Well, in this case, x is greater than or equal to 5, so it can be any number larger. And so we just say it's going to be 5 to infinity. And we would include 5 because of this. So we do a square bracket. And then for infinity, well, infinity is never included, so we always do that. Infinity is not a real number. Infinity is an idea. It's not an actual number. We can never truly reach infinity. So if it's infinity or negative infinity, it's an open bracket or an open parentheses like this. It's parentheses. My words don't work. It's fine. We're all fine. We understand what was meant. But that's our interval notation. But really, a lot of times you'll see it in that or you'll see it in this. They mean the same thing. And that's the real thing, is that these mean the same thing. These two things right here mean the same thing. These two things right here mean the same thing. These two things right here mean the same thing. And sometimes we have to do unions of them and intersections of them, all that kind of stuff. But another really important thing is when we're talking about these intervals, we want to make sure that we remember a couple of things. We want to remember that the equals sign right here implies a closed dot if we're talking about graphing it. And if it doesn't have that, then it's an open dot. It just means that it includes that. Now, one common thing students love doing, and I just want to warn you against it. Is that number line still up there? No, I can't go all the way back. Oh, well. All right, 1, 2, 3, -1, -2, -3. So I'm not going to draw them all. I'm just going to write a few of these. Okay? So let's do this. Let's say we're talking about x is strictly greater than 3. 1. The temptation students have to say, well, it's greater than 1, and then they start it right here and they go like that. And they say it's all the numbers greater than 2. I need you to understand that this is not fully representative of this. We can't just do that. A lot of y'all just think in whole numbers. Well, here's the thing. Isn't the number 1.5 bigger than 1? Well, it is. And that number's like right here. What about the number 1.1? Isn't that bigger than 1? Or what about the number 1.0? 0, 1. That's bigger than 1. If we start at the next integer and just go up, regardless of if we put an open or closed dot right here, well, what we do is we discount all these numbers. That's the importance of the open and closed dot. We want to, whatever we draw, we want to make sure it represents every number that is bigger than 1, because that's what this is representing. That's why we use the open dot. That is why we use the open dot at 1. It doesn't matter how big you draw it. It's just discounting 1 point when x is equal to 1. And everything after that. So this is the best way to represent that. So watch out for that. Don't just think in whole numbers. You've got to remember that there are an infinite number of numbers in between 0 and 1. There's an infinite number of real numbers. Okay? So there are some fancy words, but for those of you that want enrichment, there is no such bijective function that can map the set of reals to the set of integers or anything finite. Okay? It's not even countable infinity. It's uncountable. There's like a different type of infinity even between 0 and 1. And so you don't want to get rid of all those. You don't want to accidentally skip those. If you're ever interested in that, there are a ton of videos online, and I can talk about it as well, about the difference between countable and uncountable infinity if you really care about that sort of thing. It's actually super cool, and man, it is hotly debated amongst my math friends and physics friends. But anyway, if you have any questions, feel free to reach out to me or Mrs. Snyder. You can also email us, come to her office hours. I'm going to set up some office hours that I will have an optional invite for everybody and a bunch of other things. Just tell me how I can help you. And don't forget your IXL. Y'all need to take care of the diagnostic and start practicing those so you can be eligible for bonus points and extra attempts on assignments. Y'all have a fantastic day.